Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis. I'm a researcher at the SETI Institute and the Chief Scientific Officer at Unistellar. Today, we gather to talk about Psyche. Psyche, the asteroid, Psyche, the mission. We don't know yet, and we will soon know because we invited for this Anicia Arredondo. Hello, Anicia. How are you?
I'm doing very well. How are you?
Good. Where are you calling us from?
I am in San Antonio, Texas.
San Antonio, Texas. Anicia is the lead author of an article that was published recently on the metallic nature of the asteroid Psyche using the SOFIA instrument facility. We are going to talk about that in more details. Anicia is a postdoctoral researcher at the Southwest Research Institute in San Antonio, Texas, as she mentioned. And she's going to take some time to explain to us what she did. But before that, remember that you can tell us where you're watching us from. We take the time to say hello to you. And my first question for you, Anicia, is what is the scientific questions you try to answer with this study that you published recently?
Yeah, so before I answer that, I just want to lay the groundwork and kind of talk about Psyche, the asteroid in general. Of all the asteroids in the asteroid belt, Psyche, I think, is one of the weirdest. And that's because we have been studying it for a very long time. It was the 16th asteroid that was ever discovered, and we've been studying it since like the 1800s or something. And every time a new study comes out, we learn something that is shocking. And sometimes the studies contradict each other. So some studies are saying that Psyche is made of metal and it's a remnant core of a protoplanet, like how the Earth has a core and a mantle and a crust. Some people think that Psyche formed the same way, but a giant impact came and stripped the mantle and the crust away, leaving this metal hunk in space. But other people have observed Psyche with different techniques, and they found evidence of rocky material. And some people have even found evidence of hydrated material. So Psyche, just every time we observe it, we learn something different. So what I wanted to answer with my observations, I wanted to know if the mid-infrared wavelength of light, that's the same wavelength that you and I emit energy in, if that could tell us anything about the composition of Psyche. And so what we were doing is we used SOFIA, the telescope, to observe Psyche as it was rotating on its axis. And so we wanted to measure the composition at different points in the rotation and see if it was changing with rotation. And that would tell us if different parts of Psyche had different compositions.
Okay, we're going to go back to this in more details, but I just want to mention that we have people watching us from Bolivia, Fair Oaks, California, from Grand Prairie, Texas, from Louisiana in the Bayou. Hey, Ron. Ron is always watching us. That's why I say hi to him specifically. North Carolina, New Jersey in the house, Alabama, and more states. Welcome. We are talking about Psyche, the asteroid, and the true nature of this asteroid. So there is something that we need to kind of explain also, is that an asteroid, even large asteroid like Psyche, we're talking about 100 kilometers roughly in size, right? Cannot be seen well from Earth. I mean, we can use very complex adaptive optic systems and so on to see the surface and the shape, but we don't have a clear indication of the true nature of the surface. So that's the reason you wanted to use, or you used the SOFIA stratospheric telescope to observe it. Tell us a bit about what is mid-infrared and spectroscopy, and maybe why we need to use SOFIA for that.
Yeah. So different things, depending on their temperature, emit light at different energies. So like the sun emits in what we call the visible range, and that's because we can see it with our eyes. Whereas things that are cooler than the sun, like you or I, or I don't know, your dog, emit in the infrared. And that's why if we use like night vision goggles, we can see those things because that's viewing the infrared. And so we can observe asteroids in the infrared because that's actually the optimum wavelength region for them because that's what they emit in. Mm-hmm. But the Earth's atmosphere is at those wavelength ranges, the water vapor in the atmosphere just makes the data completely unusable. We can't see through at those wavelengths. And so telescopes like the James Webb Telescope in space right now, that's why it's up in space, because it had to get out of the atmosphere if it wanted to see infrared wavelengths. Mm-hmm. And then SOFIA was able to fly above 99% of the Earth's water vapor in the atmosphere. And so that's why we were able to use a semi-ground-based telescope to observe the infrared. And then spectroscopy is a technique that we use. Basically, we're observing the amount of light reflected at different energies. And so that can actually tell us something about the composition of the asteroid, because if certain minerals are present on the asteroid, they'll actually absorb all of the light at a specific wavelength. And that wavelength is specific to that mineral. It's kind of like a fingerprint. And so what we do is we take a spectrum, and it's basically energy of the light versus amount reflected of light. And we look for either dips or peaks in what should be a flat line. And then the location of those dips and peaks tell us what the asteroid or the composition of the asteroid is. And so that's what we were doing specifically at infrared wavelengths for Psyche, because that hasn't really been done before, just because it's a really hard wavelength region to observe from Earth.
Yeah, that's why we launched Space Telescope, to go above the atmosphere. And SOFIA is a remarkable instrument, I still have a hard time saying that, because it was flying 12 kilometers above the surface. So most of the atmosphere, in fact, is close to the surface, below the stratosphere. Above us, there is a very tenuous atmosphere, so there is less absorption. So did you fly yourself in the SOFIA?
I flew 14 times, yeah.
14 times. Oh, wow.
It was incredible every single time.
I did it once, and I'm super happy about that. So I can imagine 14 times, but maybe a lot. Yeah, the flights last, 7 hours? Mine lasted 8 hours. We went all the way to Hawaii and back almost.
Oh, wow. What about you? Yeah. Ours are about 12 hours each night. It's the weirdest flight you've ever been on because you take off and land at the same place. But I loved every second of it.
Yeah. I flew in it when it was still a bare airplane. So there was nothing. There was a few chairs and everything was open. So it was frightening too, because that's when you realize you're truly in a tube of metal and you cannot even see through the crack, the atmosphere. But it was a great experience.
Yeah,
so you used a forecast instrument?
Yep, that's the mid-infrared spectrometer.
Yeah, that's what I used too for the observation of Ceres. All right, great. Yeah. So when did you start this campaign?
We did all of the observations in February of 2022. And I've been working on it since then. So
wow. So that's been, you basically in February 2022, you flew 14 times, a 12 hours flight. Wow, that must have been exhausting months, I can imagine.
Well, the other flights, I also worked on a project that observed the moon in the infrared. And so some of those flights were for that. So it was all in February. Otherwise, that would be kind of horrible.
Okay, so we have more people joining us from San Ramon, California, from Ottawa, Canada, from Chaclacayo in Lima, Peru, Rio Janeiro, New Mexico, and more places around the world. Welcome. We are talking about the study of Psyche using the SOFIA Stratospheric Telescope. So what is the result? We have those spectra, a lot of them. You analyze those. So what did you get from this analysis?
Yeah, so I was talking about we're looking for dips or peaks, and the location of those dips and peaks tells you something about the composition. Well, in our spectra, they were completely flat. We saw no dips and no peaks. And so that in itself was surprising because like rocky material has a lot of features in this spectral range, and so we were expecting to see at least some of those. And so what we think is that whatever Psyche is made of has to have some composition that doesn't have any features in this spectral range. And so something that fits that description is metal. And so that supports the hypothesis that Psyche was this metal core, like the Earth's core, where the mantle and the crust were stripped away. So that's really exciting to be able to corroborate that theory, I guess. And then, like I said, we were looking for if that changed with the rotation, because previous studies at different wavelengths have seen differences with rotation, but we found none. So yeah, science is fun because even a null result is still interesting, and that's what I think is one of the coolest things about our jobs. So what
the reason I'm reacting is because we have my team published 2 or 3 years ago a paper showing Psyche, and we see some changes of color, very faint, very poorly contrasted in those images. So now you're telling us that even if you see albedo changes, maybe in fact pure metal, and those albedo changes may be just due to the reflection.
And so that's something that we were honestly shocked about. But looking more into our studies, we saw actually that as Psyche's rotating throughout and moving throughout the asteroid belt, it's actually the hemisphere that we're looking at changes. And so we found that while we were observing it, the northern hemisphere of Psyche was facing the Earth. But while a couple of previous studies were observing it, the southern hemisphere was facing the Earth. And so what we think is that maybe there is a lot of variation in that southern hemisphere, but we just happen to catch a hemisphere that nobody's really looked at before. And maybe that is less variable. And so that's really interesting, because why would it have this hemispherical dichotomy, that suggests that maybe there was like a more subsequent impacts, but only on the southern hemisphere or something.
All right. So we're going to take some questions from the audience. We already have a few of them. So please, if you have any questions for Anicia, write them in the comments if you're watching us on YouTube or Facebook, Twitch. We are on everything. LinkedIn now. So please take the time to write the comments, and we're going to take the time to ask them. We have one question from Stephen Collins here. How big would be the predecessor of Psyche have to be to have differentiation to have a metal core? So you get the question?
Yeah. That's a very good question, and one that I should know the answer to, but sadly I do not. Because most asteroids are not differentiated, and we think that most asteroids formed about 100 kilometers large. So bigger than that is a pretty safe guess, I think.
Yeah, the differentiation happened because of the internal heat capture, and also from the dissociation of radioactive elements, right? So that can take, so the size of the asteroid will basically tell you the amount of energy that you have inside the asteroid to differentiate it. There is a paper about Ben Weiss, I don't know how you say his last name, sorry, where basically he showed that if you have 1,000 kilometer asteroid, they will be all fully different. They will be differentiated, and all of them will have a core of metal. It's a paper that he published in the past to explain the existence of those M-type asteroids that could be remnant of those primitive first asteroid that was formed in the main belt. I don't know if that's still the case. This is an old paper, I said, from the 90s or the 2000s. Science has changed significantly since then. So why is it important to study Psyche? What's the motivation to launch a space mission over there, and the motivation of your research?
Yeah, so So like I said, Psyche is one of the weirdest asteroids that I know of, and I study asteroids all day, every day. I think the chance to observe what a core looks like is really, it's the only place that we can do that in the whole solar system. Like the Earth's core is, I think, 1,800 miles below the surface, and the farthest that we've ever drilled is 7.5 miles. You
Mhm.
know, we're never going to drill far enough to observe our own core, but Psyche's just sitting there and just ready to be studied. It's just an interesting object. And so I'm really excited for the Psyche mission to be going. Um, I'm excited for every single asteroid mission to an asteroid, but this one in particular, just because I think we've been to asteroids and they all look different, but this one I think is going to look much more different.
Yeah.
And I'm excited to see the diversity of all these objects.
A question from Matthew Van Horn. We said that Psyche is a metal, but what kind of metal are we talking about? Nickel, iron, something else? Do you have any idea?
Yeah. Based on its density, the expected density, yeah, it should be nickel, iron nickel.
Iron, nickel. Yes.
It should be
So,
about 30 to 60% of the volume is the estimate of the metal content.
and the density we have for this one is something like 5.5 grams EC or something like this, right?
Something,
Right.
yes.
Yes.
There's a lot of
That's
different density measurements, though. Like I
yeah.
said, every time we study it, we get something different. Um,
Yeah, I think it's one of the asteroid which has the most contradictory papers. It's a
but I like
metal.
to
It's
say
not a
that,
metal. The density is 3. No, the density is 7. I mean, I don't know who's studying the Psyche now, but it's gonna be very interesting. What we're gonna have the mission because we are going to finally get an answer to all those basic questions about the asteroid. Yes.
yeah. And I like to say it's not contradictory results. It's just telling us that Psyche is complex. And the only way to really fully understand how complex is to send a spacecraft there. So it's great.
So Rick Childers has a questions. So he wonder if it's possible to discover new elements on these heavenly bodies that will further promote science on Earth. Is it possible to find things which are very rare and exist or that barely exist on Earth or do not even exist on Earth in asteroids?
Um, I think it could be. So I'm the Psyche mission is gonna one of the instruments on it is a gamma ray and neutron spectrometer,
Mm-hmm.
and that's gonna map the elemental composition of Psyche. And I don't actually know what they're expecting to see or anything like that, but the fact that they have that on the mission means that um, maybe there could be something that we don't have a lot of on Earth.
Yeah, one of these rare elements or something like this. That's gonna
Yeah,
be interesting. Are you part yourself of the Psyche mission, or
I am not.
you're not?
I just
Okay.
really like the asteroid.
You do you have any news that you can share with us about the spacecraft?
I'm not on the team, so I really don't. I don't know. I know it launched successfully. I was watching it the other
Are you
day
watch
along
it?
with everybody
Okay.
else. Yeah.
Do you I have a question from Bezulu Kumalo? I'm sorry if I pronounce your name poorly. What do you think of mining asteroid? Is that something that we should do? What's going to happen in our time
Uh,
life?
you know, that's something that I personally have not really thought a lot about because I always assumed it would happen after my lifetime.
Okay.
But yeah, it's definitely something that's doable. I know that there's a lot of people out there who are studying, the best ways to do this, prospecting which asteroids have different materials that you might want to have in space. I personally don't know much about that, but more power to those that do.
Okay. Before we wrap up, I'm looking if there is any more questions about this research. Oh, what kind of other asteroids do you study? You mentioned that you study other asteroids. Is that you have a preference for M type, for metallic, or you study anything big? How you do between these million of targets that we have?
Yeah, I primarily study asteroids that are primitive in composition. So those are the ones that we think didn't get big enough to melt anything. And so they might still retain evidence of hydration on their surface. And so what I'm really interested in is figuring out how water was transported to Earth. And so by studying asteroids that are potentially hydrated, um, you can kind of put the pieces of the puzzle together to figure out how where they would have to be able to transport to Earth, how much water they would have to have for Earth to have its water content, stuff like that.
That's maybe you can detail a bit more about that. This is something that most people at the SETI Institute and our viewers are interested. So, are you telling us that we don't know where the water is coming from on Earth?
So there's a there's a lot of hypotheses, but um, like there's some theories that Earth's water was delivered by cometary impacts, but comets are much further out from the Earth than asteroids are. So another theory says that it could have been asteroid impacts. There's some theories that say that Earth actually formed in a region where water was abundant in the early solar system, and it didn't even need impacts. Earth, the water was just there. And so without observations of all these different objects, you can't really distinguish between those different hypotheses.
Okay. And so the study of asteroids is a way for us to find the source of water, maybe on Earth, by looking at how much water there is in some of the asteroids and what type of water. Are you interested in measuring the DH ratio, for instance?
That's one thing, yeah. There's a lot of spectral features, like I said, the different fingerprints of different materials. Water has some fingerprints, some of them in the mid-infrared, which is the region that I study. And so those are the types of features that I look for.
Okay. So I have one question for you since we keep talking about mid-infrared, mid-infrared. It's great. Mid-infrared is a great way to characterize asteroids, but we don't see a lot of mid-infrared from the ground because of water in water vapor. So SOFIA is over. JWST is the next big missions. Are you part of a JWST program? Did you manage to get time? What if yes, what are you gonna do?
Yes, I did get time. I'm very excited about that. Thank you. And yeah, I'm using it to measure the fingerprints of water in the mid-infrared. I'm going to look at two different asteroids that are on opposite sides of the asteroid belt.
Mm-hmm.
And I'm going to see if they have different amounts of water content, and then maybe that can tell us something about where they formed and therefore where water was when the solar system was forming.
Okay. Can you tell us which asteroids are those?
A couple random ones. One of them is 142 Polana in the inner belt, and the other one is 225 Henrietta in the outer belt.
Yeah, I know those. It's something like interesting that after 20 years studying asteroids, you basically have the feeling that you know like the first 2,000 of them, which is super weird when you think about it. Like you give me a name of an asteroid, sometimes I can give you the number, basically, which is super weird because we read papers all the time about them, so we see that. Okay, so this is a cycle 1 proposal, cycle 2?
This is cycle 2, yes.
Okay, so the data are not yet taken, but they're going to be taken soon?
It should be actually in about 10 days is the start of the window for my data, so I'm really excited.
Yeah, I'm going to explain the context for our viewers because most people have no idea about that. When NASA or any federal agency launch a big telescope like JWST, is not, if you want to get telescope time, it's not easy. I mean, it's not like, hey, I have this cool project, can we do that? It doesn't work like that. You have to write a proposal, right? And create a team. And there is a lot of politics as well in the proposal, who's going to be a member of the proposal and so on. So tell us about your proposal. How many people do you have? How many hours did you ask? Which instrument you use?
We're using the mid-infrared imager instrument, MIRI. And we're actually also using NIRSpec, which is the near-infrared spectrometer. And the team is about 5 people, I want to say.
Oh, nice. It's a small
Yeah,
group. Okay.
pretty small, yeah. But we all have, our very niche things that we're going to do, different parts of the project that we're going to do. So I think we come together very well. What else did you ask? I'm sorry.
Are you the PI of this or?
I am the PI, yeah.
Nice. You
This
should
has
brag a
been
bit more
scary.
about it. Come on, you're the PI of a JWST proposal. It's a great
Yeah.
thing. I mean,
This has
I'm
been my dream project for a while.
uh-huh. So so when the data arrive, again, I explained to our audience, you're gonna get an email saying that the data have been taken. Then you're gonna have an email saying that that the data are available. You download them, and with some instrument they're extremely raw, others they will be processed, right?
Mhm.
So as a PI, you basically share the data with your team, and everybody's gonna work on their niche. Or I don't know how you organize that, but it can be organic. Like it can be you have workshop, you have hours meetings every week, or everybody goes work together. How you planning to go? I should say the data are available are proprietary for like 6 months now with this
I think it's
JWST.
6 months.
Yeah.
Yeah.
So that's mean that in 6 months, if Franck Marchis wants to answer to the question you ask, he can simply go on the database and take the data and write the paper. So there's
That's
kind of
true.
a competition created in science because you have basically 6 months to finalize the analysis and publish them. So
Yeah.
good. We have a session at the AGU in San Francisco in December to talk about first observation of taken with JWST. So maybe someone will mention your observations if you're not coming. Are you coming to AGU?
I'm not coming now.
You're not? Okay. All right. Great. Yeah, that's. I'm glad we met and we have the opportunity to talk about asteroids. So next time we talk to each other will be for discussing the result of your JWST paper in a year.
Or when you steal my data, one of the two.
I will never do that. This is not something I do. I think I don't think this is something we should do, but some people do it, but I don't. All right. I really like meeting you and having the time to talk to you about Psyche, and
Yeah,
hope
thanks
to
for
see
having
you
me.
soon. All right. Thank you to all our viewers. You have an in-depth conversation between two scientists who definitely love asteroids. And Anicia is definitely leading the topic with a great result with SOFIA and soon with JWST. So I hope you're gonna continue to watch us on watch those SETI live. If you want to support us, we are a non-profit organization. You can visit our website, seti.org. Register to get our newsletter called Journey. You can also make a small donation by clicking on the buttons or go to Give Now, seti.org Give Now. Any small donation we could be used for to pay a trip for Anita to come to AGU next year to present the result of the JWST, or for me to go to San Antonio and work with with Anicia on the next big program. Anyway, we are the SETI Institute. We do more than just listening to space. We also do astrobiology. So if you want to support us, don't forget you can make a small donation. You can also follow us on social media. We are on every platform: YouTube, Twitch, Facebook. One day I'm gonna write a list myself, and visit our webpage. And if you want to support, click like this video. Tell us what you think. Let's take the time to discuss more about asteroid with Anicia, and see you soon. See you next week. Thank you very much. Bye bye.